Well, hey, Bi 11, time for a little study of ornithology, or a Latin term which means to study birds. So, we're going to push into sort of our last analysis, one of the final things we're going to look at in terms of chordates, in addition to mammals, and see what happened sort of post 65 million years ago with the asteroid impact. We know that the bird line was beginning to stem off from the Saurischian dinosaurs, and that they're endotherms and they were able to survive those cold conditions that would have been created from that significant impact, that nuclear sort of winter, if you will. But let's push on, look at our characteristics of birds and pretty well everything class Aves. Now, when we go to the course website, there's some really great stuff here. I say that every time, but it's true. I wouldn't have put it on here if I didn't really, really like it. Neat little website going over the characteristics of birds. Looking at the bird respiratory system, fabulous. They have a one-way airflow and it's extremely efficient. Unlike us, they don't breathe recycled air at all. Some of our air is coming out as we're breathing in. We can't get rid of all of the air in our lungs, which is known as our tidal volume. Birds don't have that problem, and they have a very high metabolism having to fly and take on extremely high altitudes, so they need an efficient respiratory system. Really great little mention here about dinosaur feathers and Archaeopteryx and just the significance of all of that. So let's get going with our study of the birds. So, what do we have? Well, when we look at birds, make sure that we're reflecting here. There we go. Uh, Birds are reptilian-like animals, and it's interesting because, as I say, they came off the Saurischian line. We think that mammals themselves are just evolved Saurischians, came out of this little sort of furry little rodent-like um, critter that was able to heat its body temperature and sort of ride out the effects of the asteroid impact. But birds have a lot in common with reptiles. When we look at their legs, we see that they're covered in scales. Not only that, they produce a really strong uric acid and they maintain their water balance. They're very greedy with it. They don't want to lose any water at all. So they're reptilian like with feathers, they have claws, and their front limbs are modified into wings. Even if they don't fly with them, they still have front limbs that look like that. Feathers themselves are made up of a protein. It's called keratin protein. It's similar to well, not similar to, it's the same protein that you find in your skin and that you find in your hair, secreted from these little pits in their skin. And it helps them to produce two types of feathers, which are contour feathers and down feathers. Now, in mammals, it's the hair that helps to keep us warm. In class Aves, the birds, what we see is that these really fine feathers called down feathers do a very good job of keeping the birds warm. And birds are quite waterproof as well because they cover themselves. As they preen themselves, there's a gland that they use to secrete oil and they work it all over their feathers and they make themselves quite waterproof. So there you go. There's the contour feather, which provides lifting force for when the bird flies. And you'll see this in downfilled jackets. The down feather, that's you can see that's and you'll see that's of no consequence for flying, but it's a very soft and has a sort of a large surface area type feather, and the juveniles and the newborns are just covered in it until their contour feathers come in, and that makes sense, right? Help keep them warm as they strive to survive on our planet. Now, when you look at a feather, it's really interesting. This is why the feather doesn't fly apart. Like our hair in the wind just flows. But the feather, if you look at these crisscrossing barbs, in a way, there we go. It's a little bit like Velcro connections. And there's the central vein of the feather here with these subdivisions and interlocking barbs. And it obviously provides a lot of tensile strength, enough so that when the bird flies, the structure doesn't fly apart. It gives them the lift that they require. Now, the formal name for those little guys are barbules, and they basically just hold everything together. So the evolution of the birds, we've been talking about this quite a bit. We think that they were evolving actually quite a ways back. We think that they were evolving off of sort of the perhaps the pterosaur line. So they were coming into being even during the time of the dinosaurs. Now, it's interesting, they got a lot of things in common with reptiles. You think about reptiles, you think of waterproof body, claws, and an amniotic egg. Well, we see a lot of that in the birds. The body's waterproof, yes, more or less. They have an amniotic egg, but now what they do with their amniotic egg, they put a hard shell around the outside instead of the sort of leathery, sort of rubbery shell that you see around that of the reptiles. So, let's make a note of that. The amniotic egg, same strategy, secreting uric acid. Their bones are very similar in design to the reptiles. When you see that um, the support for the limbs is supported by strong pelvic and pectoral girdles. So there's a lot that they have in common. So we'll make 3 points out of that. Oh, and one interesting point. I'm going to back up just before I move on. If you leave your car under a lamppost, let's say you're at BC Ferries, for example, and let's say you do the park and sale, you leave your car under the park and sale like I did, and you come back and it's got a great number of white splotches because the birds have defecated on your vehicle. That happened to me one time. Never park under the lamppost. I'll never forget it. What you need to know is that the white material is uric acid, so that's their concentrated urine, if you will, and the little dark spots in it, well, that's actually their feces. You have to remember that birds, just like reptiles, have a cloaca. So the urine and the feces meet in that common area and out they go. Now we have to talk about what would have been something like the first bird. If we go back, and you've probably heard of this, it's called Archaeopteryx, and it's a bird-like dinosaur. Now, interestingly enough, it had socketed teeth in its bill, feathers, a bony tail, claws on its wings, and it had a lot of the characteristics of dinosaurs. Now, I'm just going to pop out of reflection for just a second, and I just want to show you a few things that I've prepared for you. There we go. So, Archaeopteryx made quite the splash because we found this skeleton. Let's see, right here. This is a good shot of it. And I'm just going to zoom in on that. And at the time when we were expecting to find dinosaur bones, for example, they found this skeleton. And here's the head here. You could see the contour feathers show up quite nicely. And if you look at the pelvic area, you'll see that it's got a pubic bone that faces backwards. So, with a little bit of scientific work and extrapolation, what they determined we would have been looking at would have been something along the lines of this. Now, you might look at it and say ostrich or emu, but this thing was not exactly a bird that would fly. Okay, it had pivoting feet, which is quite interesting, and sort of that ostrich-like running, long fingers, curved claws, right? It has a great number of reptilian characteristics while having a great number of avian characteristics. Here's another shot which defines a few of those characteristics. The wing claw, for example, the toothed beak, and that's socketed. And if you think about it, crocodilians have socketed teeth, right? Obviously, the contour feathers are avian. Having lots of vertebrae going through the tail. Now, that's not something you see with birds, but that is something you see with reptiles. So you see this all sort of starting to line up. So one little trip around, there we go. That's what I want to see. One little trip around Google Images, we can find pretty well what we wanted to. And there you can see the pelvic array. There's the vertebrae in the tail. S-shaped neck, characteristic of birds, and it has a wishbone here in the front, sometimes called the keel, very avian-like as well. So let's pop out of that, and we'll get back to our lecture here. This comes up. Let's see. Sorry, folks. There we go. Now, this description and this controversy over Archaeopteryx has gone back and forth. But one thing is for certain, that Archaeopteryx is a reptilian bird-like fossil. We don't know if it's the missing link or if it was just one variation that was come into being at the time, but it does suggest that it's a transitional species between birds and dinosaurs. One thing that we know about birds is that they're endothermic, where the majority of the dinosaurs were ectothermic, unable to heat themselves. So this is definitely a new player, sort of on the evolutionary block. The origin of birds, it's not completely solved because, for example, we see with the hip structure a lot of similarity with with ornithischian dinosaurs, but we think that they evolved something off the pterodactyl line, and it's interesting. Were they evolving back when those two lineages were getting started, or did they just stem off of one? We're not quite sure. We're still combing through the fossil evidence. And here's what we're talking about. Here's Archaeopteryx. Based on when we found its fossil and dated it, we can place it in the same time frame. Is this the missing link? Perhaps. Or were birds just a different version of a reptile that were changing all the time? And that's where the debate rages today. So form, function, and flight. This is when it gets really interesting. Birds have some pretty amazing bodily adapted systems, really effective digesters, because they have to get as much nutrition out of their food as possible. Very high metabolism. Going alongside with a high metabolism is a respiratory system, as I've mentioned, one-way respiratory system, and they are very good at exchanging oxygen and carbon dioxide. And that's very important because they are some of their range on the planet, the places they occupy, is challenging territory. Flying up really high, you have to be able to extract oxygen very efficiently. Flight itself, watch a hummingbird. Imagine how many times the wings beat. 20, 30 times a second. And in order to sustain that level of physical output, you have to have a very efficient digestive system. And hummingbirds eat all day long to support it. They have to be extremely aerodynamic, the lightweight bones, an incredible number of mitochondria in the chest muscles. So, as I've said, they have to eat pretty well all the time. Their metabolism, being endothermic, produces a lot of heat. And the down feathers help to trap that, keep that in. And even around Prince George in the winter, you'll see crows, and they're staying warm because they're able to effectively trap the heat with their feathers. Not just down feathers, right, but their contour feathers. Now we'll get a little bit into the bodily anatomy. So in class, what we dissect is a pigeon. And it's neat because I always go back to when we first dissected the earthworm, and we see the mouth and the pharynx and the esophagus, the crop and the gizzard and everything. And when you look at a bird, you'll see that because it eats a great amount of vegetable material, it's accentuated the crop. So when a bird eats, it'll consume grains, worms, whatever it can find, and that material moves down into a crop. Now, if you ever go hunting for spruce hen, grouse, and you gut the animal and you begin to clean the animal, if you take a look in the crop, you'll find they consume a great number of pine needles, but you'll also notice in the crop that there's little stones, and they will pick little stones up off the road to consume, and they help to grind the material in the crop. It's just a digestive strategy. Not too bad. So of course our crop is going to lead down to the stomach and the rest of the digestive system for more effective transfer of nutrients. But having that crop up front, it's pretty interesting what they're doing. Last time we saw a crop like that, you could go back to the earthworm, where the crop was like a loading area before you got down to the grinding gizzard. And you're seeing that structure, that whole strategy come up again. Okay, come down to the stomach. Now, the stomach itself is more or less two chambered, and that's a traditional structure. The top is like a loading area, and the bottom is for a lot of the mechanical digestion. So, the first chamber of the stomach, you might say it's like seeing a crop and a gizzard again, because the stomach really is a crop and a gizzard, right? Loading and grinding. It's in the bottom of the stomach where you'll find the rugae. There's these folds, and as your stomach grinds, when you feel your hunger pangs, that's the rugae in the stomach, and you'll feel them pushing and grinding on each other in the bottom of your belly there. You'll find a small intestine and a large intestine. And at this point, the small intestine, the first portion is doing exactly what it does in us, the duodenum. It's assisting with digestion, and absorption largely happens in the rest of the remainder of the small intestine, in the ileum and the jejunum, until you lead out through the large intestine at the end, and you come out into the cloacal area, right? And the cloacal area up here is the kidney, right here, which is very good. Theirs is extremely well adapted at conserving water. And if you notice, here is the ureter leading down and boom, coming out in the cloacal area. So undigested food, basically waste, will be expelled with the uric acid, so you'll get a white and brown paste. Leaves a mess behind. That's why you're not supposed to feed the birds at Starbucks or at cafes, because as they eat, they just walk around and poop, right? Don't worry, they'll get a meal someplace else. You don't have to feed them. Now, we want to look at, this is my favorite part of the lecture, is the one-way flow of air through a bird's respiratory system. Now, this would be something for Olympic athletes, wouldn't it? Where you're only getting an exchange of fresh air, and the recycled air, the let's say the used air, is just released without getting in the way, if you will. Now, that's really good for a metabolic rate. This would be like a gasoline-powered engine, only getting fresh air, oxygen. The fuel is burned that much more effectively. So it gives them the ability. You have to have respiratory systems like this at high altitudes where the air is thin, um, or for that matter, when a hummingbird is exercising and flying and fluttering around. It's got to have really effective energy production to be able to sustain that metabolic activity. So I'm going to pop out of reflection for just a moment, and I want to show you that. That's some pretty neat stuff. And the birds, boop, 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 there it is. We'll go to the animation, and I'll go through the step through here. So what you're looking at, the respiratory system of the bird, is pretty neat. These are what you would expect to be the lung. You hold it out in your hand, and it's an interesting organ. And what it looks like, let's see here. See if I can show you it exactly. It appears to have like these little ridges running through it. And we dissect a pigeon. And let's see if I can find one that's been extracted. There we go. And you look at it like this and you wonder, well, what are those ridges? Why does it have that appearance? Why does it look like that? Well, these are tracheal tubes. So if we go back to this animation here, this is essentially what you're looking at here. And there's sacs that go all around the edge of the lung. Okay, so what happens? When the bird initially takes a breath, the air comes down the trachea and there's posterior air sacs. So they're drawing as if it's one thing. So these fill full of fresh air, And then that's called inhalation one. And then those sacs collapse and they pass in this direction over these tracheal tubes. Now that's where the exchange of fresh air happens. Now, as the air passes through the tracheal tubes, it's stored in the anterior air sacs. Okay, so that's inhalation two. Now, the release of air is always exhalation, so that was exhalation one. Okay, so inhalation one, exhalation one, inhalation two, and then exhalation. So what happens is, if you follow my cursor, the air flows in here, passes over here, and then out. It's really an amazing respiratory system. Here's the first half. There's the exchange, and then the anterior air sacs will receive the tired air, and then on exhalation two, they'll simply release it. There's a really good, I've got a YouTube video for that right here, bird respiratory system. If you want to see it basically running live, uh, click on this animation right here. But having a respiratory system like that, that's pretty amazing. That enables you to have a much higher metabolic rate. Um, let's just put it this way: the muscles can fire on all cylinders, no problem. Their nitrogenous waste, we've already talked about this. That strong uric acid, right? It's that awful paste they leave, generally kind of a white color, right? They're very good at reabsorbing water because if you think about their metabolisms being as high as they have to absorb water because they need it for metabolism. So that's a leftover trick, right? Putting them another piece of evidence that they're um, closely related to their reptilian cousins who do exactly the same thing. Now, in order for birds to be able to take advantage of flight, they had to have fairly light bones. Now, interestingly enough, if you look at penguins, they don't have these lightweight bones because, well, they don't really need them. Penguins are birds that fly through the water, and it's not an advantage for them. They never developed these bones where they've got a lot of hollow space and these little struts that go this way and that to provide structure. Now that you have to realize, so I'm going to zoom in on that again a little bit. This is why you don't feed your dog cooked chicken bones because those little struts once they're heated to the point, let's say like Kentucky Fried Chicken, if you feed it to them, they become very brittle, and when they bite through the bone, these little bone shards can get lodged in the basically it in their esophagus, and that could be a major problem. So the bones are strengthened by the struts, and they make very lightweight for the birds. So, ladies and gentlemen, this is the end of my lecture on birds. I hope you enjoyed, and have a good one. I'm out.